Welcome to The Explainer. Today, we are getting our hands dirty, figuratively of course, and diving right under the hood. We're going to break down the science of how engines stay cool and find out why there's no one-size-fits-all solution.
So get this, the average engine in your car, it's actually incredibly inefficient. Around 70% of the energy it gets from fuel doesn't even move the car. Nope, it's just wasted as pure raw heat.
If all that heat just sat there, it would literally melt the engine from the inside out. I mean, total meltdown. And that simple, dangerous fact brings us to the absolutely ingenious world of engine cooling.
Okay, so let's really dig into this fundamental challenge. This isn't just some minor detail for engineers. It is the central problem they have to solve for any engine to work.
You can really think of this excess heat as the main villain of our story today. The entire purpose of a cooling system is to manage this thermal energy, to keep it from warping, melting, and destroying the engine's super precise metal parts.
So, what was the very first and simplest solution engineers came up with? Well, they turned to the most abundant and, let's be honest, cheapest resource you can find, the air all around us.
The basic idea here is just simple physics. It's a process called convection. Heat naturally wants to move from a hot object, like an engine block, to the cooler air that's touching it. The bigger the temperature difference, the faster that heat just jumps away.
Now just picture a simple, flat piece of metal on an engine. As air flows over it, it can only touch that one flat surface. It's not a lot of contact, which really limits how fast you can pull heat away.
And the solution to that is as simple as it is brilliant. You add fins. These thin metal ridges completely change the game by dramatically increasing the surface area. This means way more air can make contact with the engine at once, pulling heat away much more effectively. And the beauty of this system is that it's so wonderfully simple and cheap. You don't have pumps, you don't have a radiator, there's no coolant to worry about. That's exactly why you see it on so many smaller commuter motorcycles. But its big weakness is that it's totally passive. If you get stuck in traffic and the air stops moving, well, so does the cooling.
Air cooling is great for the outside of the engine, for the parts you can see. But the absolute most intense heat builds up deep inside the engine's core, around things like the piston, where there's no way for outside air to get to.
And that problem brings us to the next step in the evolution of engine cooling. It's a pretty clever system that uses something that's already inside every engine to begin with.
Yep, we're talking about engine oil. In these systems, the oil gets a second job. Its main role is still to reduce friction and lubricate everything, but here it also acts like a little heat-soaking courier, absorbing all that thermal energy from the hottest parts deep inside.
The crucial difference here is adding one extra component, an oil cooler. You can basically think of it as a small radiator. Hot oil gets pumped out of the engine and through this cooler, where airflow cools it down before it gets sent right back in to absorb even more heat.
Now, an oil cooler is a huge step up, for sure, but it still ultimately relies on outside air to do the cooling. And that leads us to the most advanced, most precisely controlled solution of all, full liquid cooling.
So here's the key. Water, which is the main ingredient in coolant, has a much higher specific heat capacity than oil. In plain English, that just means it's a way more efficient heat sponge. The same amount of coolant can absorb and carry away a lot more heat than the same amount of oil can. It's not even close.
And this, right here, is the real magic of a modern cooling system. See, by sealing and pressurizing the whole system, engineers can raise the boiling point of the coolant from the normal 100 degrees Celsius to 120 degrees Celsius, or even higher. This is what stops the coolant from just turning into steam when a high-performance engine is really working hard.
What you get is this powerful, closed loop that gives engineers incredible control. Coolant flows through special channels in the engine block, soaking up intense heat. A pump then pushes that hot coolant to the radiator. Air flowing through the radiator cools the liquid down, and then it flows right back to the engine to start the cycle all over again, keeping the engine in that perfect temperature sweet spot.
Okay, so we've seen all three cooling strategies in action. Now, let's put them all side by side for the final verdict.
This table really just sums up the whole trade-off, doesn't it? Air cooling is simple and cheap, perfect for a basic engine. Liquid cooling is complex and expensive, but it offers the absolute best performance for powerful engines. And oil cooling? It provides that smart, effective middle ground.
So the biggest takeaway here is that each one of these systems exists for a really good reason. There is no single best solution. There's only the right solution for a specific engine, and it's always a balance between cost, complexity, and performance.
So there you have it. We hope this gives you a whole new appreciation for the clever and absolutely critical engineering that's happening right under the hood every single time you're on the road. Thanks for joining us.